We've seen some simple classes of algorithms, constant, log, linear, and we didn't do log linear, but we'll do that one in a little while. The next class are polynomial complexity, and the most common here are quadratic. The complexity grows with the square of the size of the input. Again, I want you to see what are some of the characteristics that lead to that kind of algorithm. And one of the things we're going to see here is that this commonly occurs when we have nested loops or recursive function calls inside of the algorithm. And we need to say that in a way where the recursive function call has some costs other than constant. Because as we saw with factorial, you can have recursive function calls and have it still be linear. As before, let's look at some examples and see the characteristics that lead to this kind of behavior. Here's a simple algorithm. I want to explain it, but again, I'm less concerned about what it does. I'm more interested in showing you what the pattern is that leads to this. So this is an algorithm that given two lists of elements, could be numbers, could be something else, but given two lists is going to try and decide, is the first list a subset of the second list? Meaning, every element of the first list, does it also occur in the second list, even though there may be other elements inside the second list? Let's look at the code and the characteristics of the code, and then let's analyze it. So this starts by taking an element in the first list. It's going to set up a little flag here that initially says, I don't yet have a match. And then given that element from the first list, it's going to loop over all the elements of the second list, asking, do I have an instance of that element in the second list? If I find one right here, I'm going to set that flag to true and break out of that loop. Once I've broken out of that loop, I then test, and having set match to true, the if not match doesn't hold, and so I don't return false. I go back around to the loop and get the next element of the first list. On the other hand, if I go through all of this search here and don't find a match, then the matched flag is set to false, and when I come to this test, I'm going to break out of the entire thing by returning false. If I get through the entire set of the list L1 and I've found a match in all cases, in that case I'm going to return true. Now you notice here, I've got nested loops. I've got an outer loop on L1, I've got an inner loop on L2, and even though I could break out of either of those lists, either here or here, we know that it's the worst case behavior that we're interested in, and that's going to happen when in fact L1 is in fact a subset of L2, because I'm going to search through all of L1 looking for that solution. Key thing I want you to do if I step back from this is to notice here I've got a nested loop, a loop inside of a loop. And that's characteristic of quadratic complexity, and let's see why. So if I take my code, I can now ask, what is the order of growth here? First of all, I know that the outer loop is generally going to be executed the length of L1 times. So however many elements there are in L1, let's call that, for example, n, is going to execute that loop n times. Because it's going to ask for each element, does it have a match? Yes, it's possible it could stop earlier, but in the worst case, it's going to go through all of them. What else do I know? I know that for each outer iteration, for each element in L1, I'm going to go through this inner loop, this loop, up to the length of L2 times. And in fact, in the worst case, I am going to go through it up to the length of L2 times. So, what do I have then? I've got an outer loop, I do length of L1 times. For each one of those, I do length of L2 kinds of operations. And by our multiplication law, we know that that basically says this order of growth is the product of the length of L1 times the length of L2. Okay? What's the worst case? The worst case is when they're both of the same length. And in that case, again, let's just call that n. We're going to do n squared operations, n times n operations. And as I said, the fact that we might break out of the loop earlier doesn't change the order of growth of the algorithm. The worst case is basically quadratic in the length of the list. You've seen the characteristic, nested calls, or nested loops is a nice characteristic of something that's inherently quadratic in complexity. Here's another example. I want to find the intersection of two lists, and then I want to return a list where each element appears only once. So L1 is a list of things, could be numbers, could be something else. L2 is similarly a list, and I'm going to first start by trying to find a list that has those that appear in both lists. And then because there might be some duplication, I'm going to clean it up and only return a list where the elements appear exactly once. I'm not going to step through the code in detail, but notice again a nice common pattern. There's a nested pair of loops. And what I'm doing here makes sense. I set up a temporary variable called TMP for temp. For each element of loop 1, I run through all the elements of loop 2, asking, is that element from loop 1, from list 1 rather, in list 2? And if it is, I add it into temp. I just append it to the end of that. Once I've done all of that, I'm going to clean it up by setting up a new temporary variable called res for result. And then running through the things that appear in both lists, I simply say, if I haven't already put it into the result, add it in, but I'm not going to duplicate it if it appears more than once. And then I'm going to return the result, res down here. Key characteristic, I've got a bottom loop, that's just a loop. I've got a nested pair of loops here. And we've already seen in our earlier example, that's probably an indication of the quadratic performance. So let's look at it. There's my code, and here's what I know. That first nested loop, by exactly the same analysis I did with the early example, is going to take length of L1 times length of L2 steps. Because for every element of L1, I do however many elements there are in L2 number of steps. And here there's no breaking out of it earlier. So it's literally going to be, I do length of L2 steps for every element in L1, so therefore the product of those two lengths. The second loop, the bottom, just goes through at most length of L1 number of steps, if every element of L1 also appeared in L2. So now I've got a case of two different orders of growth. The first one's quadratic, the second one is linear. That second term, as we make the problem size really large, simply gets overwhelmed by the first term, and so we ignore that second term, and we simply say this is quadratic in that product of length of L1 and length of L2. And again, worst case is in essence when they're both of the same length, and we'd say this is order n squared. So a nice example of a quadratic complexity algorithm. Characteristic, nested loops. Now, that can happen in a wide range of cases. Here's simply another example where now I'm simply doing something that's going over a range. And the only difference here is that that range may get generated incrementally as I need it, but otherwise this is exactly like the two cases I saw before. What do I want to look at here? I want to look at what's the cost of the first loop, which is I want to do it n times because of that range. And then what's the cost of the second loop? I'm also going to do it n times because of that range. So it's n times n. Again, it's order n squared. You see the characteristics of quadratic complexity algorithms.